beyond the edge of light, where galaxies fade into shadow, something vast and unseen stirs in the cosmic dark. Not random voids or chance alignments, but immense, structured silhouettes stretching billions of light years, too large to exist, too ordered to be accidental. They defy the laws we trust, haunting the outer limits of space, like echoes from another reality. What if these forgotten structures are not errors in data, but cracks in our understanding? A glimpse into a deeper architecture of the universe, silent, ancient, and watching. In 2003, in the quiet hum of a Princeton data center, a flicker passed across a screen so subtle it might have been dismissed as static, as error, as nothing at all. But within that flicker, buried in the oldest light in the universe, was a whisper that would unravel certainty. The Wilkinson microwave anisotropy probe, WMAP, had just delivered its first full map of the cosmic microwave background, the afterglow of creation, a radiant echo from 380,000 years after the Big Bang. To most eyes, it was a triumph, a near-perfect snapshot of an infant universe, smooth and isotropic, just as theory predicted. But to Dr. Neil Urozik and his team, one feature refused to settle into harmony. At the largest angular scales, fluctuations, stretching more than 60 degrees across the sky, the expected ripples in temperature were unnaturally subdued. The deep bass notes of the cosmic symphony had been silenced. These low multipoles, the dipole, quadrupole, and octopole moments, should have been randomly oriented, scattered like stars across an infinite night. Instead, they aligned, not by chance, not by coincidence. They fell into a plane, slicing through space with eerie precision, and worse. That plane corresponded disturbingly closely with the orbit of our own solar system. It was dubbed, half in jest and half in dread, the axis of evil. The name carried weight far beyond irony, for what it implied was not merely an anomaly, but a fracture in the foundation of modern cosmology. The cosmological principle, the unshakable assumption that the universe is homogeneous and isotropic on large scales, that no direction is special, no location privileged, now faced its most unsettling challenge. Here, in the pristine relic radiation that predates galaxies, stars, even atoms, was evidence of a preferred axis, a cosmic alignment so statistically improbable that the odds of its occurring by chance were less than 0.1%, and yet, there it was, by 2013, when the Planck satellite released its higher resolution, noise-filtered maps of the CMB. The scientific community braced for clarity. Surely, with superior instrumentation, the anomaly would dissolve, revealed as an artifact of WMAP's calibration, or galactic foreground contamination, or some overlooked systematic error. But Planck did not erase the axis, it confirmed it with colder precision. The data revealed the same suppression of large-scale power, the same alignment between the quadrupole and octopole, the same uncanny correlation with the ecliptic plane, the flat disk in which Earth and the other planets orbit the Sun. And now, with greater sensitivity, another revelation emerged: patterns in the CMB that mirrored structures in the present-day universe. Vast clusters of galaxies, supervoids, hundreds of millions of light-years across, seemed to cast faint shadows on the primordial sky imprints, not of the early cosmos, But of the late dot, how could formations existing billions of years after the CMB was emitted leave traces upon it? One possibility lies in the integrated Sachs-Wolf effect, a subtle gravitational phenomenon where photons of the CMB gain or lose energy as they traverse evolving gravitational potentials in an expanding universe. In regions dominated by dark energy, such as vast cosmic voids, this effect can produce measurable cold spots in the microwave background. Observations have indeed linked the CMB cold spot, a region of unusual temperature depression, to a supervoid located roughly 3 billion light-years away. But the scale of coherence remains troubling. That a structure from the relatively recent universe should align so precisely with anomalies imprinted at the dawn of time suggests a continuity of order that transcends epochs. More disquieting still is the implication of non-Gaussianity deviations from the random, bell-curve distribution of fluctuations expected in standard inflationary models. The axis of evil exhibits just such deviations. Its correlations are too clean, too geometric, too structured to be the product of quantum randomness stretched across space. Some researchers, analyzing the statistical topology of the CMB, have found evidence of planar symmetry, rotational coherence, and even hints of mirror-like reflection across the ecliptic plane. Could the universe, at its deepest level, possess a hidden geometry, one that resists the assumption of randomness? Inflation, the leading theory for the universe's first fraction of a second, predicts a nearly invariant Gaussian spectrum of fluctuations born from quantum noise. But if inflation ended unevenly or occurred within a pre-existing anisotropic spacetime, the result could be residual alignments frozen into the CMB models, such as anisotropic inflation or vector field-driven expansion. Propose mechanisms by which a preferred direction could be imprinted during the universe's birth. Though speculative, these theories are mathematically consistent and increasingly testable. Even more radical interpretations have surfaced. What if the axis of evil is not a feature of our universe, but a boundary between universes? In the framework of eternal inflation, our cosmos may be one bubble among countless others in a vast multiverse. If a neighboring bubble universe collided with ours in the earliest moments of expansion, the impact could have left a scar, an asymmetric imprint across the CMB, localized along a plane of contact. Simulations by physicists like Stephen Feeney and Matthew Johnson have shown that such collisions would produce disk-like distortions in temperature and polarization, potentially explaining both the cold spot and the alignment of low multiple. The timing fits. Such a collision would have occurred before recombination, leaving its mark directly on the photon-baryon plasma. And if multiple collisions happened, they might generate coherent interference patterns, echoes overlapping like ripples on a pond, resulting in the kind of large-scale order now observed. But then comes the deeper unease. Why does this axis align so closely with our solar system? Is it possible that we occupy a position not just in space, but in meaning? Most scientists reject such implications outright. The human instinct to find significance in alignment is strong, but the universe, they argue, does not revolve around us. More likely, the correlation is coincidental, or the result of incomplete foreground subtraction. Our Milky Way's dust, magnetic fields, and synchrotron radiation all contaminate CMB measurements, especially near the galactic plane. Could the axis be a ghost of our own galaxy's influence? Perhaps. Yet repeated analyses using different cleaning algorithms, frequency bands, and masking techniques continue to recover the anomaly. Even when galactic emissions are meticulously removed, the quadruple alignment persists. The cold spot remains. The suppression of large-scale power refuses to vanish. And now, telescopic surveys of the actual distribution of galaxies have begun to reflect the same asymmetry. Data from the Sloan Digital Sky Survey and the Dark Energy Survey reveal that galaxy clustering is not perfectly uniform. On scales approaching 1 billion light-years, there are indications of bulk flows, entire superclusters moving coherently toward a region dubbed the Great Attractor, and beyond it, the even more massive Shapley supercluster. But these motions exceed predictions from CDM cosmology. Their velocity and direction suggest gravitational influences from sources beyond the observable horizon mass concentrations, so distant their light has not yet reached us, if it ever will. This dark flow hypothesis, controversial but not ruled out, implies that the universe extends far beyond what we can see and that its structure is shaped by forces operating outside our causal domain. If true, then the axis of evil may not be an illusion, nor a flaw, but a horizon effect, the faint pull of unseen mass warping the fabric of space on a scale so grand it bends the very definition of locality. Another clue emerges from the polarization of the CMB. Planck mission measured not only temperature but also the orientation of light waves, its E modes and B modes, providing a second layer of information about the early universe. Intriguingly, certain polarization patterns exhibit anomalies that correlate with the temperature-based axis. This cross-verification strengthens the case that the signal is real, not instrumental. Moreover, studies of radio galaxies using telescopes like NVSS and later ASCA have detected a similar alignment in the polarization angles of distant quasars, a phenomenon known as cosmic bias. Across billions of light-years, the planes of polarized light appear subtly rotated, as if passing through a universe-wide magnetic field or interacting with axion-like dark matter particles. The axis of this rotation aligns, once again, with the ecliptic plane. Coincidence or convergence? Each dataset, CMB temperature, CMB polarization, galaxy clustering, radio polarization, bulk flows, points toward the same unsettling conclusion. The universe is not as random as we believed. There is a thread running through it, a silent rhythm connecting the smallest quantum fluctuations to the largest structures in existence. And perhaps, just perhaps, that thread leads back to a time before time. Some theorists speculate that the axis of evil may be a remnant of pre-Big Bang physics, a fossil from a prior phase of cosmic evolution. In conformal cyclic cosmology, proposed by Roger Penrose, the distant future of one universe becomes the Big Bang of the next through a rescaling of spacetime. In this model, supermassive black holes from the previous eon evaporate via Hawking radiation, leaving circular imprints in the CMB known as Hawking points. Penrose and colleagues claim to have identified several such rings in Planck data, clustered near the same regions as the cold spot. and the axis, if correct. Then the forgotten structures are not merely distant, they are ancient, beyond time, echoes from a cosmos that died before ours began. Yet science demands skepticism. Extraordinary claims require extraordinary evidence. And so, the debate continues. Was the axis of evil born from instrument error, galactic contamination, a statistical fluke amplified by human pattern-seeking minds? Or is it something else entirely, a sign that the universe possesses a hidden architecture, a skeleton beneath the skin of space-time, visible only in the faintest whispers of ancient light? As new observatories prepare to launch the Simons Observatory, CMBs 4, Light B RD, the resolution of the CMB will sharpen further. We may finally determine whether the axis dissolves under scrutiny or deepens into revelation. Until then, it remains not loud, not violent, but persistent, a quiet crack in the mirror of cosmology, a suggestion that the universe, in its deepest layers, may not be indifferent, that it may carry memory, that it may, in some ineffable way, remember where it came from and where it is going, and that we, peering into the afterglow of creation, may have stumbled upon the edge of a truth too vast to hold. For over a century, cosmology rested upon a quiet certainty that the universe, at its deepest level, is impartial, that no direction holds dominion over another, that from any vantage point, on scales large enough, the cosmos reveals the same face, star-strewn, galaxy-dusted, evenly scattered across the void. This is the cosmological principle, the silent foundation beneath every equation, every simulation, every grand narrative of cosmic evolution. It was born from observation, refined by theory, and sealed into doctrine by the success of the Big Bang model. The universe, it seemed, had no center, no edge, no favored axis, only endless repetition, a vast, indifferent tapestry woven from uniformity. But now, the fabric is tearing at distances exceeding 10 billion light-years. Astronomers have detected structures so immense, so precisely aligned, that they defy not only measurement, but logic itself. Filaments of galaxies stretching across the observable horizon. Clusters arranged in sheets and walls, with geometries too coherent to be random. One such formation, the Hercules-Corona Borealis Great Wall, discovered in 2013 through gamma burst mapping, spans an estimated 10 billion light-years, nearly 1/8 of the entire observable universe. Another, the giant arc, revealed in 2021 using data from the Sloan Digital Sky Survey, curves gracefully across the sky for 3.3 billion light-years, a celestial ribbon of galaxies suspended in gravitational harmony. These are not mere collections of stars. They are architectures, organized, persistent, and impossibly large, and their existence poses a question that echoes through the halls of physics like a struck bell. How can something so vast come to be, if no part of it could ever have touched another? According to Einstein's laws, nothing, not matter, not energy, not information, can travel faster than light. In the 13.8 billion years since the Big Bang, no signal has had time to cross more than about 93 billion light-years, the diameter of the observable universe. Yet, within that sphere, regions separated by billions of light-years exhibit synchronized structure, motion, and alignment. Galaxies spin in coordinated patterns. Clusters flow toward common centers, temperature anomalies in the CMB mirror distributions in the late universe. It is as if to minds isolated on opposite ends of eternity. Heart of inflation theory. The prevailing explanation for the universe's large-scale smoothness. In the first fraction of a second after the Big Bang, space expanded exponentially faster than light itself, stretching quantum fluctuations into the seeds of galaxies while erasing any primordial irregularities. The result should have been a homogeneous cosmos, where no structure exceeds roughly 1.2 billion light-years, the theoretical limit imposed by causal horizons before recombination. Yet here, again and again, are formations twice, 3 times, even 8 times that size. Either inflation failed, its smoothing effect incomplete, or our understanding of causality is incomplete. Some theorists propose that these structures are illusions, artifacts of projection, statistical flukes magnified by human pattern recognition, but repeated analyses, cross-verified with independent datasets from Wise, Planck, and DESI, continue to recover them. Their statistical significance grows stronger with each survey. They do not fade under scrutiny. They deepen, perhaps. Then they are not within the universe as we know it, but beyond it. One radical hypothesis suggests that what we perceive as colossal cosmic formations may actually be gravitational projections, shadows cast by mass concentrations, located outside the observable universe, like ripples on a pond whose source lies beyond the shoreline. Their influence seeps into our domain through gravity, which, unlike light, may extend beyond horizons in ways not yet fully understood. Modified gravity models, such as those incorporating non-local fields or higher dimensional leakage, as in Branyard scenarios, allow for such effects. In these frameworks, space-time is not strictly bounded by the speed of light. Gravitational potentials can leak across cosmic divides, imprinting order upon chaos. Even more unsettling is the possibility that these structures are remnants of a pre-Big Bang era, fossils encoded in spacetime before the dawn of time as we know it. Conformal cyclic cosmology (CCC) posits that the universe undergoes infinite cycles, each beginning with a Big Bang and ending in an infinitely expanded, empty state. Through a mathematical rescaling of spacetime, the remote future of one eon becomes the hot, dense beginning of the next. In this model, supermassive black holes from the previous universe evaporate via Hawking radiation, leaving concentric rings of low entropy in the CMB, what Penrose calls Hawking points. Several such rings have been identified in Planck satellite data, clustered in regions coinciding with the cold spot and the axis of evil, if true. Then the great walls and arcs we observe may not be products of this universe's evolution, but echoes of structures that existed before it. Their coherence would not require causal connection within our timeline, because their origin lies in a prior phase, where different rules applied. Another interpretation emerges from eternal inflation and the multiverse hypothesis. In this view, our universe is one bubble among countless others, nucleating within an eternally inflating meta-universe. If neighboring bubbles collided during their early expansion, the impact could have left a planar distortion in spacetime, a scar visible today as a vast, coherent structure aligned across the sky. Simulations show that such collisions produce temperature, anisotropies, polarization, asymmetries, and large-scale flows consistent with observed anomalies. The cold spot, the Hercules-Corona Wall, could they all be fragments of ancient cosmic wounds? Or worse, signs that our universe is not self-contained? The implications are philosophical as much as physical. To accept that structures larger than causality permit exist is to admit that the universe may not be a closed system, that information, form, perhaps even history, leaks in from elsewhere, that what we call the cosmos is merely a room in a mansion we cannot see. Further evidence comes from dark flow, the observation that hundreds of galaxy clusters are moving in a coherent direction at velocities unexplained by local mass distributions. Data from the cosmic microwave background and X-ray cluster surveys reveal bulk motions exceeding 1,000 kilometers per second toward a region near the constellations Centaurus and Vela. These movements cannot be accounted for by known matter, dark or otherwise, within the observable horizon. Something massive, something unseen is pulling, and whatever it is, it lies beyond sight. NASA's Chandra X-ray Observatory and the Planck collaboration have independently confirmed the anomaly. Though controversial, the persistence of dark flow across multiple instruments suggests it is real. And if real, it implies a gravitational source so distant, so enormous, that its light will never reach us, trapped forever beyond the cosmic horizon in such a universe. Isotropy is not a law, but an illusion born of limited perspective, like sailors who believed the ocean flat until the horizon curved. We may have mistaken the limits of observation for the boundaries of truth. Even the distribution of quasars tells a story of hidden order. In 2014, a team analyzing radio-loud quasars found that their spins were statistically aligned over distances exceeding 3 billion light-years, an alignment that mirrored the very filaments of the cosmic web. Since quasar orientation depends on the angular momentum of their host galaxies, this suggests that galactic rotation itself may be influenced by forces operating on scales far larger than any known mechanism can explain. Could large-scale magnetic fields, primordial and interwoven with space-time, guide the spin of galaxies like compass needles in a forgotten field? Or might quantum entanglement, scaled to cosmological proportions, create correlations that transcend distance? Emerging theories in quantum gravity suggest that space-time itself may be entangled at fundamental levels, that the connectivity of the universe arises not from proximity, but from shared quantum states. In this view, two regions of space, though separated by billions of light-years, could remain correlated if they originated from the same quantum fluctuation. Such entanglement could manifest as synchronized structure, offering a non-local explanation for the coherence of giant cosmic formations. But then comes the deeper unease. If the universe is not isotropic, if it possesses preferred directions, hidden axes, external influences, then what does that mean for us? Are we, by chance, located near a cosmic fault line? A boundary where one universe meets another? A region where the veil between realities thins? Or is the alignment with our solar system the eerie correlation between the axis of evil and the ecliptic plane, not coincidence, but consequence? Most scientists resist such notions. The anthropic instinct to find meaning in alignment is strong, but the universe, they argue, does not revolve around Earth. Yet the data does not vanish with dismissal. It lingers, accumulates, whispers, and perhaps the most humbling possibility is not that we are central, but that we are peripheral, that our universe is not the whole story, but a fragment, a single note in a symphony, played across dimensions we cannot perceive. As new observatories prepare to map the cosmos in unprecedented detail, the Vera Rubin Observatory scanning the sky nightly, the square-kilometer array listening to the faint hum of neutral hydrogen, Lisa preparing to detect gravitational waves from the earliest moments, the mystery of the forgotten structures may finally yield, or it may deepen, because what if the largest structures are not meant to be seen? What if they exist only in gravity's shadow, in the silence between photons, in the spaces where mathematics breaks down and intuition fails? They stand at the edge of knowing, like mountains seen through fog, their peaks lost in cloud, not shouting, not demanding attention, but they're immutable, ancient and watching, not with eyes, but with geometry. In the silent expanse beyond Orion's belt, where starlight thins and galaxies blur into smudges of ancient glow, a filament of light curves across space like a bridge built by gods. It stretches unbroken for 3 billion light-years, a cosmic crescent arcing through time and darkness, too graceful to be chance, too vast to be real. In 2021, Dr. Alexia Lopez found it not in direct view, but in shadow, in the way distant quasars dimmed as their light passed through clouds of intergalactic gas aligned along a single sweeping curve. These absorption lines, imprinted on spectra like fingerprints on glass, revealed the presence of a structure so immense it defied the known limits of gravity, of time, of causality itself. They called it the giant arc, and it should not exist, according to the standard model of cosmology, built upon Einstein's general relativity and the framework of cold, dark matter. The largest structures that can form in the universe are constrained by physics itself. Before recombination, when the universe was a hot, opaque plasma, sound waves rippled through the dense medium, setting an upper limit on how far matter could coalesce under gravity. This ceiling, known as the Baryon Acoustic Oscillation Bow Scale, sits at roughly 490 million light-years in diameter. Those simulations allow for filaments up to about 1.2 billion light-years before coherence breaks down. Beyond that, no connected structure should survive the expansion of space, the randomness of initial fluctuations, or the finite speed of information. Yet the giant arc spans more than twice that length. Its curvature follows no known gravitational potential. There is no central mass, no cluster, no black hole capable of bending such a vast ribbon of galaxies into its elegant arc. It does not conform to the expected flow of the cosmic web, not quite. Instead, it appears almost sculpted, as if some invisible hand had drawn it across the sky, or as though space-time itself had been gently warped from outside. Then came the Hercules-Corona Borealis Great Wall, discovered earlier in 2013. Through the clustering of gamma-ray bursts, cosmic lighthouses marking the deaths of massive stars, this formation dwarfs even the giant arc in sheer scale. Stretching over 10 billion light-years, It occupies nearly 1/10 of the entire observable universe. To visualize, it is to confront the collapse of imagination, a continuous sheet of galaxy clusters, superclusters, and intervening filaments, all arranged with improbable coherence across a volume so large that light has not had time to cross it since the Big Bang dot in a universe governed by causality. Such unity should be impossible. Regions at opposite ends of the Great Wall are separated by distances exceeding the particle horizon, the maximum range over which any physical influence could have traveled. They never touched, never interacted, never exchanged energy or information, and yet they share structure, pattern, order. It is as if two shores, divided by an ocean wider than time, were shaped by the same tide. These discoveries did not arrive quietly. They erupted through the data like cracks in a dam, flooding observatories and simulation centers with doubt. The Sloan Digital Sky Survey (SDSS), mapping over 1 million galaxies in 3 dimensions, began revealing more anomalies: walls, voids, sheets that clustered not randomly, but along planes and axes that echoed across billions of light-years. The Dark Energy Survey Day, designed to probe the acceleration of cosmic expansion, found instead evidence of bulk flows, entire superclusters drifting toward, their motions too synchronized, too directional, to be explained by local mass alone. Something was pulling something vast, and it was not visible. Gravitational lensing, the bending of light by mass, offered a clue. Images from Hubble and later the James Webb Space Telescope revealed subtle distortions in the shapes of distant galaxies, warps in space-time that persisted even after accounting for all detectable matter. These weak lensing maps painted a ghostly scaffold beneath the visible cosmos, diffuse halos of mass, stretching between clusters, forming bridges and nodes far larger than any known galaxy group. This was the dark backbone of the universe, not merely dark matter, but dark structure, a hidden architecture underlying the luminous web. Some researchers proposed these were remnants of primordial density waves, frozen in place from the first instance of inflation. Quantum fluctuations, stretched to cosmic proportions, might have seeded irregularities large enough to birth superstructures beyond current theoretical limits, provided inflation lasted slightly longer or varied in intensity across space. But another possibility loomed. What if these colossal formations are not within our universe, but at its boundary? String theory and Branyard cosmology suggest that our four-dimensional space-time may be embedded within a higher dimensional bulk, a realm where other universes float like islands in an infinite sea. In such models, gravity can leak into the bulk, allowing distant regions of our universe to feel influences from adjacent branes. More dramatically, collisions between branes could imprint planar disturbances, membranes of energy and curvature that manifest as coherent structures in our cosmos. The giant arc, with its unnatural curvature, bears resemblance to the predicted signature of a brane intersection, a slice where another universe grazed ours in the early epochs, leaving behind a ripple in geometry. Similarly, the linear alignment of the Hercules-Corona Wall echoes simulations of topological defects formed during symmetry phase transitions in the infant universe, like cracks in ice spreading across a Pond. These are not mere analogies. In field theories of cosmology, such defects, cosmic strings, domain walls, textures can persist across eons, acting as gravitational attractors around which galaxies cluster, while individual cosmic strings remain undetected. Networks of them could generate large-scale alignments indistinguishable from observed superstructures. A 2023 study published in Physical Review demonstrated that a network of superconducting cosmic strings formed during a grand unification phase transition could reproduce both the angular coherence of the giant arc and the statistical excess of galaxy clustering along the Great Wall. Even more unsettling is the implication of non-local gravity. Einstein's theory assumes locality, that space-time curvature depends only on nearby mass and energy. But quantum gravity models, including loop quantum gravity and certain formulations of entropic gravity, allow for non-local correlations where distant regions influence each other without direct contact. If space-time emerges from a deeper quantum substrate, then large-scale coherence may not require causal connection in the classical sense, but rather shared entanglement in the underlying fabric of reality. In this view, the forgotten structures are not built, they are remembered. Patterns preserved in the quantum memory of space-time. Further evidence emerges from the polarization of the cosmic microwave background. Planck satellite data shows anomalies in E-mode and B-mode signals that align spatially with the locations of the giant arc and the Great Wall. Though faint, the correlation suggests a deep continuity between the early universe and its late-time structure, one that cannot be explained by standard hierarchical clustering alone. Could these superstructures be projections, gravitational echoes from a pre-inflationary era? Some physicists, inspired by Penrose's conformal cyclic cosmology, propose that what we see as giant walls may actually be conformal shadows, imprints of supermassive black holes from a previous eon. Their final Hawking radiation bursts, seeding concentric ripples in the new universe's spacetime. These would appear as circular or arc-like enhancements in galaxy density, precisely matching the morphology of the giant arc. Others point to anisotropic inflation, a variant of the inflationary model in which expansion proceeded faster in certain directions than others, creating preferred axes in the distribution of matter. Computer simulations run at the Perimeter Institute show that even mild anisotropy during inflation can produce filamentary structures exceeding 5 billion light-years in length, with curvatures mimicking those observed. But none of these theories fully resolve the tension, because the deeper one looks, the more the universe resists simplicity. Hubble and Webb lensing maps continue to reveal mass concentrations that do not align with visible galaxies. Diffuse, extended halos, too large for clusters, too structured for randomness, linger at the edges of surveys, like footprints leading off a cliff. The dark energy camera has detected coherent shear patterns in deep fields that extend beyond the reach of known matter distributions, suggesting the presence of dark sheets, two-dimensional layers of invisible mass shaping the cosmos on scales previously unimaginable. Are these the skeletons of forgotten universes, or the boundaries of our own? One speculative but mathematically consistent hypothesis proposes that the largest structures trace the edges of cosmic voids. In a multiverse foam, a sponge-like arrangement of bubble universes expanding into one another. Where bubbles collide, their interfaces compress matter and energy, forming thin, dense shells that appear as great walls to internal observers. From within, such a wall would seem like a natural formation, but from outside, it would be recognized for what it is, a border, if true. Then, the Hercules-Corona Wall is not a structure in space, but a limit of space, a horizon not of time, but of being. And every observation that confirms its existence brings us closer to a truth, both humbling and terrifying, that the universe may not be self-contained, that it may have edges, boundaries, neighbors, that we may live not in a boundless void, but within a cell of something greater, as new instruments prepare to scan the cosmos with unprecedented depth. The Simons Observatory probing the CMB's finest wrinkles. The Vera Rubin Observatory set to photograph the entire southern sky every few nights. Lisa poised to listen for gravitational waves from the dawn of time. The question grows louder. Are we seeing the universe as it truly is? Or are we glimpsing its reflection in a shattered mirror? For now, the giant arc remains in the data. The Great Wall stands in the maps, unmoved, unexplained, too large to ignore, too coherent to dismiss. They do not shout. They do not flare. They simply are silent, immovable, etched into the dark, like runes left by a hand we cannot see. And perhaps, in their stillness, they carry a message that the cosmos is not random, that order exists beyond understanding, and that the greatest structures in existence may not be made of stars, but of silence, of shadow, of the spaces between what we know and what lies beyond. By 2030, the silence of deep space had begun to speak in riddles. From the high Atacama Plateau, where the Simons Observatory pierced the thin Andean air, and from the Antarctic ice beneath which CMB's 4 listened to the universe's first light, a new whisper emerged, subtle, precise, and profoundly disorienting. In the polarization of the cosmic microwave background, the faint orientation of photons, released 380,000 years after the Big Bang, scientists detected patterns not of randomness, but of interference. Delicate fringes, like the ripple marks left by overlapping waves on a still pond, threaded through the oldest light in existence. These were not predicted by standard inflation. They bore no signature of known foregrounds or instrumental artifacts. Instead, they resembled the telltale scars of a collision, a moment. In the earliest instance of time, when our universe struck another, a bubble collision. In the theory of eternal inflation, the cosmos is not a single expanding fireball, but an infinite foam of universes, bubbles nucleating within a perpetually inflating metarealm. Each bubble is a separate universe, with its own laws, constants, and dimensions. Ours, it is theorized, formed when a local region of this inflating field decayed into a lower energy state, triggering what we call the Big Bang. But if bubbles form close together, they can collide before drifting apart, their boundaries merging in a violent exchange of energy and geometry. Such collisions leave imprints. Simulations show they generate circular polarization anomalies in the CMB concentric rings of twisted E modes and B modes, localized along the plane of impact. The patterns detected by Simons and CMBs matched these predictions with unsettling fidelity. Some rings were partial, as if only grazing our cosmic horizon. Others stretched across vast swaths of sky, their centers aligned not with the galactic plane, nor the CMB, but with the very regions where the largest large-scale structures reside: the cold spot, the giant arc, the Hercules-Corona Wall. It was as if the universe had been scarred, and the wounds followed the bones of its forgotten architecture. These findings did not stand alone. They arrived amid a growing crisis in cosmology, one that had simmered for over a decade but now threatened to unravel the foundations of measurement itself. The Hubble tension dot. For years, two values of the Hubble constant, the rate at which the universe expands, refused to reconcile. Local measurements based on type, Ia supernova, and Cepheid variables observed by Hubble and later Webb consistently yielded a value around 73 kilometers per second per megapascal. But data from the Planck satellite, extrapolating backward from the CMB under CDM assumptions, gave a lower figure, 67 kilometers per second MPC. The discrepancy, once attributed to observational error, persisted with increasing statistical significance, now exceeding 5 sigma, the gold standard for discovery in physics. Something was wrong, and the most unsettling explanations pointed not to faulty instruments, but to a flawed assumption that the universe is homogeneous and isotropic on large scales. What if, instead, we reside near the center of a vast underdensity, a cosmic void stretching hundreds of millions of light-years across? In such a region, matter would be sparser than average, leading to weaker gravitational pull from surrounding areas. This would cause galaxies within the void to recede faster relative to distant observers, an effect known as the Hubble bubble scenario. From within, it would appear as though the universe were expanding more rapidly than it actually is on global scales. This could explain the higher local Hubble constant, not because expansion is accelerating faster, but because we are in a gravitational well that distorts our perspective. But then came deeper questions. Could there be many such voids nested, fractal-like, forming a hierarchy of emptiness and density that extends far beyond the observable horizon? Computer models incorporating scale-invariant structure formation suggest yes. In certain modified gravity theories and non-Gaussian inflation scenarios, the distribution of matter resembles a cosmic foam, clusters and filaments wrapping around voids within voids, some exceeding 1 billion light-years in diameter. If true, then the observable universe may not be a perfect sphere centered on Earth, but a lopsided lobe, warped by external mass concentrations, its shape subtly distorted by gravitational fields originating from realms whose light will never reach us. The Copernican principle that we occupy no privileged position had long shielded cosmology from existential doubt. But now, the data whispered otherwise. Not that we are central, but that we are asymmetrically placed, embedded in a region shaped by forces beyond sight, observing a cosmos whose uniformity may be nothing more than a local illusion. Gravitational lensing maps from JWST and Euclid reinforced the suspicion. Weak distortions in background galaxy shapes revealed coherent shear patterns extending across billions of light-years, too large to be explained by visible mass, too structured to to be random noise. These gradients suggested a preferred direction in space-time curvature, a tidal force pulling gently but persistently from one sector of the sky. When overlaid with CMB polarization anomalies, the alignment was uncanny. The same regions showing interference fringes also exhibited the strongest deviations in lensing shear. Coincidence or connection? Some theorists proposed that these effects arise from bulk flow induced by superstructures beyond the horizon gravitational titans whose influence leaks into our domain despite causal separation. Others ventured further that the interference patterns are not imprints on the CMB, but evidence that the CMB itself passed through layered spacetime regions where quantum fields oscillate at different frequencies, like light moving through stacked sheets of glass. This led to a radical reinterpretation. Perhaps the forgotten structures are not merely massive, they are topological, boundaries between phases of spacetime, like the surface of a soap bubble separating inside from out. If our universe is one such bubble, then its walls may be defined by these colossal formations, membranes of dark energy, cosmic strings, or vacuum transitions, invisible except through their gravitational and polarizational influence. In this view, the giant arc is not a filament of galaxies, but a horizon-scale defect, a crack in the symmetry of inflation, frozen into place at the birth of time. The Hercules-Corona Wall is not a collection of clusters, but a brain interface where our universe once touched another. And the cold spot is not a supervoid, but a wound, the fossilized impact site of a collision with a neighboring cosmos. Even time itself may bear the strain. CMBs for detected minute variations in the redshift of primordial photons, not due to motion, but to shifts in the gravitational potential along their path. These integrated Sachs-Wolf signals were strongest in regions coinciding with the largest voids and walls, suggesting that dark energy behaves differently across space. Rather than being uniform, it may cluster, fluctuate, or even evolve in response to underlying structure. This violates the cosmological constant hypothesis, the cornerstone of CDM, and hints at a dynamic, responsive vacuum energy, possibly linked to scalar fields predicted in string theory. Worse still, the interference fringes in polarization suggest that spacetime may possess a layered history like sedimentary rock, built up in epochs we cannot access directly. Each fringe could represent a past interaction, a fleeting moment when another universe brushed against ours, leaving behind a ripple in the quantum vacuum. Over eons, these ripples interfere, amplify, cancel, creating the complex patterns now emerging from the noise. And if multiple collisions occurred, they might generate standing waves in spacetime itself, resonances that persist today as coherent, large-scale flows, bulk motions, and anomalous alignments. But the most unsettling implication remains unspoken until the quietest moments of analysis. What if the observable universe is not all there is, not just in size, but in shape? General relativity assumes a simply connected, spherically symmetric spacetime on large scales, but nothing mandates this. Solutions to Einstein's equations allow for multiply-connected topologies, universes, with handles, tunnels, or edges. Some models propose a Poincare dodecahedral space, where space wraps back on itself. Others suggest a toroidal, or elliptical geometry. If true, the largest structures we see might not be distant objects, but repeated images of nearer ones, lensed around a curved cosmos. Yet the interference patterns resist such explanations. Their scale exceeds any plausible wraparound distance. Their alignment with external mass gradients suggests an origin outside the system, which brings science to the edge of a forbidden thought, that the universe has boundaries, not edges in space, but limits in structure zones where physics changes, where causality frays, where other realities press close, and we, nestled within a distorted lobe of spacetime, may be feeling their pull. The forgotten structures, once dismissed as statistical flukes, now appear as sentinels, marking the perimeter of a domain we barely comprehend. They do not glow. They do not explode. They simply warp the rules, bend the light, skew the numbers, whisper in the static. By 2035, a consensus began to form, not in textbooks, but in hushed conference rooms and late-night simulations. The universe is not isotropic. It is not homogeneous. It may not even be self-contained. The cosmological principle, so long revered, may be a useful fiction, a simplification that worked until we looked too closely. Now we look, and what we see defies symmetry. There are directions, gradients, edges, not of matter alone, but of meaning. Because to accept that the universe has a shape, shaped by external forces, is to accept that we live inside, something like cells, within a body, unaware of the organism they compose. Perhaps the greatest mystery is not what lies beyond the horizon, but what lies beyond understanding and weather. In the twisted polarization of ancient light, we have finally found proof that we are not alone, not in life, but in existence. In the silence between stars, where data streams cool into meaning, science began to dream in higher dimensions, faced with structures too vast to form, alignments too precise to be random, and a cosmic microwave background scarred by interference patterns that defy locality. Researchers turned not to incremental fixes, but to the most radical frameworks ever conceived. For when observation shatters assumption, theory must leap across the chasm of disbelief. And so, from the ashes of certainty, rose visions of reality far stranger than fiction. A multiverse entangled at birth, an eternal cycle of dying and reborn universes, membranes colliding in unseen dimensions, and a cosmos folded back upon itself like a Mobius strip of Spaceable. Each offered a window into the forgotten structures, those ghostly filaments, walls and voids stretching billions of light years across the sky. But none delivered finality, only echoes, hints, shadows on the cave wall of understanding. Among them, one idea emerged from quantum cosmology with quiet force: quantum entanglement across universes, proposed by physicist Dr. Laura Mersini-Houghton. This hypothesis reimagines inflation not as a solitary event, but as a quantum process in which our universe was once entangled with others before decohering, breaking connection as space expanded. In this model, the primordial vacuum was not empty, but a seething network of correlated fluctuations spanning multiple nascent universes. When inflation ended locally, disentanglement occurred, not cleanly, but with residual imprints frozen into the geometry of spacetime. These imprints, she argued, manifest today as the large-scale anomalies in the CMB, the suppression of power at low multipoles, the axis of evil, the alignment of quadrupole and octupole moments. They are not signs of flawed instruments or galactic contamination, but fossilized quantum correlations, etched into the fabric of the observable universe, like scars from a birth that was never fully solitary, if true. Then the forgotten structures are not objects within space. They are distortions of space, born when our universe let go of another. Like two droplets separating in slow motion, their surfaces still trembling from contact. The cosmos retains a memory of its twin, and what we see in the giant arc, the cold spot, the Hercules-Corona Wall, may not be matter at all, but regions where quantum disentanglement warped the gravitational potential, guiding galaxy formation along lines written before time began. It is a vision both elegant and haunting, that the largest structures in existence were never built by gravity, but inherited from a deeper layer of reality, one where separation is illusion and connection persists beyond causality. Another path leads backward through eons, past heat death, beyond the end of time. Roger Penrose's conformal cyclic cosmology (CCC) proposes a universe without beginning or end, a sequence of infinite cycles, each called an eon. In this model, the remote future of one universe dominated by massless particles and infinite expansion becomes mathematically identical to the hot, dense state of the next Big Bang through a rescaling of space-time geometry. The transition is seamless, though unrecognizable. All matter decays. Black holes evaporate via Hawking radiation, and only information remains, but not silently. When supermassive black holes merge in the late stages of an eon, they release bursts of energy concentrated in spherical waves of gravitational radiation. As the universe transitions to the next cycle, these bursts become imprinted on the new cosmic microwave background as circular depressions in temperature. Hawking points, Penrose, and collaborators have claimed statistical evidence for such. Rings in Planck, satellite data, clusters of concentric anomalies preferentially located in regions coinciding with the cold spot and other large-scale voids. More provocatively, the perimeters of great walls. Could it be that the forgotten structures are not formations of this eon but ghosts of the last? That the great walls are not accumulations of galaxies, but the fossilized shock fronts of evaporating black holes from a prior eternity? In this view, the universe does not forget, it recycles. And in the silence after entropy wins, it begins again with memories encoded in geometry. Each Hawking point would mark the final sigh of a cosmic titan, now reborn as a seed for new structure. Voids in our sky might be the graves of ancient singularities. Filaments, the ripples they left behind. There is no death, only transformation. But if CCC speaks of cycles, brain cosmology speaks of neighbors. Inspired by string theory, this framework imagines our universe as a three-dimensional membrane, a three-brain floating within a higher dimensional space known as the bulk. Other brains may drift nearby, invisible yet massive, their presence felt only through gravity, which can propagate into the bulk, unlike the forces confined to our BRANE. In this scenario, what we perceive as the origin of the cosmos, the Big Bang, might not have been an explosion in space, but a collision between brains. Such an impact would send shock waves rippling across the surface of our membrane, compressing matter and energy into coherent sheets and filament structures indistinguishable from the giant arc or the Hercules-Corona Wall. Simulations conducted at Stanford and Cambridge show that a head-on brain collision generates planar disturbances propagating outward at near light speed, leaving behind a preferred axis and large-scale temperature anisotropies in the CMB precisely matching observed anomalies. Moreover, repeated glancing collisions could produce concentric polarization fringes, akin to those detected by Simon's Observatory and CMB's 4. The implication is staggering. The forgotten structures may not be products of internal evolution, but impact zones, the bruised edges where our universe touched another. We do not live in isolation. We live in proximity, and somewhere in the bulk, another cosmos drifts close, perhaps even now brushing against us in ways we cannot see, but whose gravitational shadow shapes the fate of galaxies. Yet there is a quieter, more introspective possibility, one that requires no multiverse, no prior eon, no extra dimensions, only curvature. Einstein's equations allow for non-trivial topology, spacetime, geometries that loop back on themselves. Just as Earth appears flat locally but is globally spherical, the universe might seem infinite while actually being finite and closed. Solutions such as the Poincare dodecahedral space or the 3D suggest that light could travel around the cosmos, returning to its origin after billions of years. If so, distant objects might be reflections of nearer ones, multiple images of the same structure seen through bent paths in space. Could the forgotten structures be illusions, our own galaxy clusters, glimpsed through light that has circumnavigated the universe? This idea, though speculative, gained traction when astronomers noted unexpected repetitions in the distribution of quasar absorption, lines, and galaxy cluster morphologies. Some superstructures appear mirrored across opposite sectors of the sky, with similar redshifts and orientations, while conventional explanations attribute this to projection effects. A small but growing body of research explores whether these could be topological images, real but duplicated, like stars reflected in a hall of mirrors. If true, then the 10 billion light-year span of the Hercules-Corona Wall may not violate causal limits because it isn't truly that long. It is shorter, wrapped. Its apparent enormity, an artifact of perspective. We would not be seeing separate entities, but echoes, our past, looping back to meet us. But even this elegant solution falters under scrutiny. The scale of coherence exceeds plausible topological scales predicted by CMB constraints. The Planck collaboration placed tight limits on universal curvature, finding it flat to within 0.2%. A small universe capable of producing visible wraparound effects should have left unmistakable signatures in the CMB's low multipoles. None have been conclusively found. Still, absence is not denial, because what if the topology is not global but patchy? What if spacetime folds unevenly, creating localized loops near regions of extreme density or dark energy concentration? Modified gravity theories incorporating non-local operators or quantum corrections permit such geometries. In these models, light doesn't travel around the whole universe, but around parts of it, guided by dark energy gradients or quantum vacuum fluctuations, then the forgotten structures could be both real and illusory, physical formations. Yes, but also amplified by recursive lensing, their light passing through the same regions multiple times, building up apparent coherence, like a whisper echoing in a cathedral, heard not once, but many times over. Each theory, entanglement scars, conformal fossils, brain impacts, topological mirages, offers a different language for the same mystery. None can yet claim victory. All remain tentative, held aloft by mathematics, sustained by anomaly, and perhaps that is the point, for in their very plurality, they reveal something deeper than physics, a crisis of perception. Science assumed the universe was neutral, uniform, self-contained. But the data whispers otherwise. There are directions, boundaries, histories beyond ours, connections beyond space. To accept any of these theories is to abandon the Copernican ideal, not because we are central, but because we are embedded, caught in a web of influences that stretch beyond sight, beyond time, beyond dimension. The forgotten structures stand at the edge of knowledge, neither fully revealed nor entirely hidden. They do not answer. They only deepen, dot-like footprints leading into fog, like signals from a sender we cannot name. And as new observatories prepare to scan the polarized sky with unprecedented resolution, Lisa, listening for primordial gravitational waves, ska mapping hydrogen across cosmic dawn, CMBHD, hunting for subdegree fringes, the question grows heavier. Are we interpreting noise, or are we finally learning to read the scars of creation? One truth remains constant. Whatever the forgotten structures are, they were not meant to be seen. They exist at the limit of detection, at the edge of logic, where equations falter and imagination trembles. And in their presence, science does not conquer mystery, it bows before it. In the high Atacama Desert, where the sky bleeds into black each afternoon and stars burn with preternatural clarity, a new eye has opened upon the cosmos. The Vera C. Rubin Observatory, activated in 2025, stands like a sentinel at the edge of Earth's breath. Its mirror, 8 meters wide, gathers light from depths no human has ever charted. Night after night, it scans the southern sky, capturing images of galaxies so distant their light began its journey when Earth was still molten rock. Over 10 years, the Legacy Survey of Space and Time, LSST, will map more than 20 billion galaxies, constructing a three-dimensional atlas of the observable universe with unprecedented resolution and depth. And within that vast archive, scientists search for an answer to a quiet, terrible question. Do the forgotten structures end? The giant arc, the Hercules-Corona Borealis Great Wall, the cold spots, shadowy void. These formations stretch to the limits of current detection so large they brush against the boundary of what can be seen. But what lies beyond? Do these walls continue folding into even vaster geometries? Or do they terminate abruptly like cliffs at the edge of a world? If they end too cleanly, too symmetrically, it would suggest something unthinkable. Not just that the universe contains anomalies, but that it may possess boundaries. Not edges in space, perhaps, but transitions, zones where density, expansion rate, or even physical law shifts. Such features would not appear in starlight alone. They would reveal themselves in the motion of galaxies, the warping of space-time, the subtle distortions of light across eons. That is where Euclid and the Nancy Grace Roman Space Telescope enter the silent siege, launched in succession. These orbiting observatories now drift in the cold halo around L2, far from Earth's glare. Their mission: to measure weak gravitational lensing across billions of galaxies, tiny, cumulative bends in light caused by the invisible hand of mass. By analyzing how background galaxies are stretched into faint arcs, Euclid and Roman trace the dark scaffolding of the cosmos, the hidden web of dark matter and unseen energy that shapes all visible structure. But they look for something more. They search for coherent tidal forces, patterns in the sheer field that point not inward toward clusters, but outward, away from the center of the observable sphere, a uniform pull in one direction, a gradient in space-time curvature that cannot be explained by local mass. Such signals would imply that our region of space is embedded within a larger gravitational context, an external field, perhaps generated by superstructures beyond the horizon, or by the asymmetric geometry of a cosmic bubble. Preliminary data, released in 2028, hinted at just such an anomaly. Across a swath of sky aligned with the cold spot and the axis of evil, lensing vectors showed a statistically significant deviation. Galaxies, subtly skewed as if tugged by a force originating from outside. Not strong, not violent, but persistent, like leaves drifting toward the edge of a pond. It was not proof, but it was a whisper. Meanwhile, beneath the Swiss-French border, deep within the tunnels of sea, another kind of search unfolds, one not of light, but of vacuum. Particle physicists probe the stability of the Higgs field, the quantum entity that gives mass to everything. According to theory, the universe exists in a metastable vacuum state, not the lowest possible energy, but a precarious valley in a vast landscape of potential. A localized fluctuation, a quantum hiccup, could trigger a phase transition, a bubble of true vacuum expanding at light speed, rewriting physics as it goes. Could such fluctuations have occurred in the early universe? And might their remnants still linger, frozen into spacetime as sharp boundaries between regions of differing vacuum energy? Some models suggest yes. A 2027 paper in Physical Review Letters proposed that domain walls formed during electroweak symmetry breaking could persist as ultra-diffuse shells, invisible except through their gravitational influence on galaxy clustering and CMB polarization. These Higgs brains would not emit light, but could act as barriers, defining the edges of cosmic voids, shaping the distribution of superstructures, even mimicking the curvature of the giant arc. The idea remains speculative, yet it bridges the infinitesimal and the infinite, a particle-scale event echoing across 10 billion light-years at the same time. Artificial intelligence has become a silent partner in the hunt. Neural networks, trained on simulations derived from loop quantum gravity, string cosmology, and non-Gaussian inflation models, now sift through petabytes of observational data not to confirm known theories, but to imagine new ones. These AI systems test whether modified initial conditions during inflation's slight vector fields or multi-field dynamics can produce the observed alignments. suppressed low multipoles and colossal filaments without violating causality. Early results are unsettling. Certain configurations, such as a brief period of anisotropic expansion followed by rapid isotropization, can generate structures resembling the Great Walls, while remaining consistent with finite signal speeds. Others suggest that quantum entanglement on cosmological scales could allow coherence without communication, preserving the appearance of order across causally disconnected regions. But none eliminate the mystery. They only reframe it, because even if the forgotten structures can be simulated, the deeper question remains: why this particular order? Why these alignments? Why now? And then, from the radio silence of remote outback Australia and South Africa, another signal rises: the square-kilometer array, fully operational by 2030, listens not to light but to the hum of space-time itself. Spread across thousands of kilometers, its dishes and antennas form the most sensitive radio telescope ever built. Tuned to ultra-low frequencies, it searches for nanohertz gravitational waves, ripples in the fabric of reality, potentially generated by cosmic strings, primordial black hole mergers, or even collisions between universes in the earliest moments of inflation. Such waves would not come from stars or galaxies. They would be relics of events predating recombination, echoes of the universe's first convulsions, imprinted in the polarization of the CMB or in the timing of pulsars scattered across the Milky Way. In 2031, the SKA collaboration announced tentative evidence of a stochastic background signal, faint, pervasive, and coherent across hemispheres. Its frequency spectrum did not match known astrophysical sources. It bore resemblance instead to predictions of cosmic string networks or brain impacts. Events so energetic they warped space-time on universe-scale dimensions. If confirmed, it would mean the forgotten structures are not static. They are scars of motion, of violence, of contact, of something happening long ago and still reverberating together. These instruments form no grand declaration, no triumphant announcement. Instead, they wage a silent siege, a decade-long campaign of observation, simulation, and speculation against the unknown. They do not assume answers. They assume only that the universe speaks if one learns to listen, and slowly a picture begins to emerge, not of chaos, not of randomness, but of structure, layered, recursive, extending beyond the edge of light. The LSST reveals that the giant arc does not fade gently into darkness. It terminates abruptly along a plane that aligns with the CMB's coldest region. Beyond that boundary, galaxy density drops sharply, not gradually, defying models of smooth clustering. The Hercules-Corona Wall, once thought isolated, appears connected to other filaments in a web-like arrangement that spans nearly half the observable sky, suggesting a single, coherent system too vast to have formed under standard CDM evolution. Euclid detects tidal gradients that increase with distance, stronger at redshift z greater than 2, weaker nearby, as if the pole originates from a source receding with time. Roman observes subtle birefringence in polarized light from distant quasars, with rotation angles correlating precisely with regions of anomalous lensing. Shear.ai simulations begin to favor models where inflation ended unevenly where quantum fluctuations were amplified along preferred axes. The SKAS gravitational wave background strengthens, peaking in directions coinciding with the cold spot and the axis of evil. Each thread pulls tighter. Each clue points outward, not to error, not to illusion, but to reality deeper, darker, and more structured than imagined. And yet, no single instrument dares to claim victory. No theory unifies them all. The siege continues because truth at the frontier is not found in a flash, but in the slow accumulation of whispers, in the tremor of a photon's polarization, in the bend of a galaxy's shape, in the silence between stars. And in that silence, a question lingers, no longer scientific, but existential. Are we mapping the universe? Or are we tracing the walls of a chamber we never knew we occupied? One thing becomes clear. The forgotten structures were never meant to be ignored. They were left behind as markers, as warnings, as echoes from the edge of everything. We once believed the universe was simple, a grand, elegant machine born in fire, expanding with order, governed by laws as immutable as stone. We trusted that, given enough time and light, we could map its every contour, decode its origins, predict its end. The cosmos, we thought, would yield to mathematics, to observation, to reason. But now, at the outermost edge of sight, where photons grow thin and time stretches into silence, that certainty dissolves. There, rising from the dark, like ruins of a forgotten age, are structures too vast to be real. Filaments spanning billions of light years, walls of galaxies aligned with impossible precision, voids so deep they seem carved by absence. They do not flicker in the noise. They do not vanish under scrutiny. They persist, etched into the sky, written in gravity, imprinted on the oldest light. And they do not merely challenge physics. They unsettle the soul. For what are we, if not creatures of pattern? Beings who find meaning in symmetry, comfort in continuity. We built cathedrals to align with stars. We named constellations from scattered points. And now the universe returns the gesture, not with answers, but with riddles written on a scale that humbles even our most audacious theories. The forgotten structures suggest that reality extends beyond what light can carry, that the observable universe is not the whole story, but a single frame in an infinite film, that history may stretch backward before the Big Bang through eons we cannot touch, into cycles of creation and collapse older than time itself, that we may not be alone in the multiverse, but one ripple among countless others, each born from collision, decay, or quantum fluctuation, or worse, that we are not central even to this universe, that we reside in a quiet corner, a lobe of space-time gently warped by forces beyond perception, near the edge of a void, close to the boundary of a bubble, caught in the gravitational tide of something so distant it exists only as a whisper in the data. Perhaps the cold spot is not empty space, but the shadow of another cosmos pressing against our own. Perhaps the giant arc is not a filament of galaxies, but the fossilized impact of a brain collision, a wound in space-time from an event that occurred before inflation smoothed the sky. Perhaps the Hercules-Corona Wall does not mark the largest structure ever seen, but the edge of what can be seen, the threshold beyond which our physics fails, and new laws begin, and perhaps in the interference fringes of the CM, we are not seeing noise, but echoes, ripples from a prior eon. As Roger Penrose proposed, where supermassive black holes evaporated into information, seeding the next cycle with concentric rings of memory, if true. Then the universe does not forget, it remembers, not in images, but in geometry, in the curvature of space, in the alignment of galaxies, in the silent pull of unseen mass. And if it remembers, then who is to say it does not know? Not consciously, not with thought, but with structure, with coherence, with pattern, with the subtle persistence of form across eons. We speak of the Copernican principle as if it were law, that we occupy no privileged place. But what if the opposite is true? Not that we are central in space, but that we are awake, that among all the dust and fire, we are one of the few places where the universe has turned its gaze inward, where matter has become aware of itself, where light has learned to ask questions. We are not masters of this cosmos, we are witnesses, standing beneath skies thick with ancient starlight, peering into depths no human was meant to see, guided not by instinct, but by wonder. And wonder does not diminish with knowledge, it grows. For every answer science uncovers, 10 new mysteries unfold. The Hubble tension leads to cosmic voids, which lead to bubble universes, which lead to collisions in higher dimensions. The axis of evil gives way to quantum entanglement across realities. The great walls dissolve into topological folds, only to reappear as tidal gradients pointing outward toward something always, toward something, and in that endless unfolding, humanity finds its place, not as conqueror, not as interpreter, but as witness to beauty, to scale, to the sheer improbability of existence. Because the universe could have been silent, it could have been random, it could have been cold and indifferent, with no patterns to find, no questions to ask. But it is not. It is structured, it is strange, it is strange, it is coherent in ways we do not yet understand. And that coherence, that faint signal beneath the noise, suggests something profound. That the cosmos is not just physical, it is meaningful, not in the sense of purpose handed down, but in the sense of connection of threads running from quantum fluctuations to galaxy clusters, from the first moment to the last, from one eon to the next. We do not know what the forgotten structures are. We may never know, but we know this: they are real, they are vast. They are watching us back, not with eyes, but with presence, like mountains seen through fog. They shape the landscape simply by existing, and perhaps, in their stillness, they carry a message that we are not alone, not because there are others like us among the stars, but because the universe itself is alive, with history layered, recursive, eternal, and in the silence between galaxies. As light from the edge of time finally reaches our telescopes, we hear it, not a voice, not a signal, but a rhythm, the echo of time folding back on itself, an endless cycle of birth, death, and rebirth written in the bones of space, and we, fleeting and fragile, stand within it, breathing, seeing, remembering, and hoping against all odds that the universe, in its deepest layers, remembers us too.